Let us first complete this exercise, of which we have done the first three parts. So this is the fourth one. It tells us that the ideal quotient of this intersection of some ideals II and some ideal J is equal to the intersection of these ideal quotients. Here we may have infinitely many ideals II or finitely many, it's a general intersection. It's actually quite easy, so let's see the solution. Okay, so we start the solution like this. We first take any element in this ideal quotient. So let that element be x. Then by the definition of this ideal quotient, xj is a subset of the first ideal, which in this case is an intersection. So because xj is a subset of this intersection, so xj would be a subset of each ideal II, because this intersection itself is a subset of each II for each I. Now from this condition we directly get the fact that x belongs to this ideal quotient II colon j for each I, and that is why x will belong to the intersection of these ideal quotients, and that way any element in this ideal quotient is also an element in this intersection of the ideal quotients. So that is why this is a subset of this. Now we are going to prove the reverse inclusion. Firstly, we take any element y in this intersection of ideal quotients. Then obviously y will belong to each such ideal quotient. Y belongs to II colon j for each I. But then by the definition of this ideal quotient, yj will be a subset of II for each I. But then if yj is contained in every II, then it is also of course contained in their intersection. So that's how we get this. But then from this condition we directly get this, because this tells us that yj should be contained in the first ideal of this ideal quotient. So that way any element here is also here, and that is why this is also a subset of this. Now combining this containment and the previous one, you get equality. So that is part 4. Next let us see part 5. So this is part 5. In part 5 we have this ideal quotient where the first ideal is I and the second ideal is this sum of some ideals ji. Note that unlike product of ideals, when you consider sum of ideals, infinitely many ideals may be involved. You already know the definition. So that will be equal to the intersection of these ideal quotients. This is slightly different from this one. Here the first ideal was changing, here the second ideal is changing. So let's prove this. So we start the proof or the solution, you can call it anything because it's an exercise, so solution. So we start it by choosing any element from here. Say x is any element here. Then by the definition of this ideal quotient, x times this ideal, this sum, would be a subset of I. And that is why x times ji is a subset of I for each I. Why? Well, that is because the ideal ji is itself contained in the sum of all the ji's. That's why. But then what does this tell you? This immediately tells you that x belongs to this ideal quotient of I and ji for each I. And that's why x belongs to their intersection. So that way any element here is also present here. So we have proved that this is a subset of this. And then we will go for the reverse inclusion. Okay, so next we write the conclusion here that this is a subset of this. Conversely, we take an element here. Let that element be y. Then of course, y will belong to each such ideal quotient I colon ji, and that is why yji will be a subset of I for each I. Now we are going to choose some finitely many indices arbitrarily, and these indices are actually coming from that set over which this I is changing. Okay, whatever index set is there in the background, from there we are arbitrarily choosing indices but finitely many. And we are actually going to consider those j's ji1, ji2 up to jin, and from each one of them we are choosing one element arbitrarily, b1 from ji1, b2 from ji2, like that, bn from jin, and then we consider y times y is our this element, the sum of these b's. By the extended left distributive law, this equals this yb1 plus yb2 up to ybn. Now this belongs to I. Why? Because of this thing. If you take y times any element from ji, that product will of course be in yji, and because of this containment that will also belong to I. That means each such yb is in I, and because I is an ideal, it's a group under addition, so this sum also belongs to I. Now we have this. How do we conclude this from this? Recall how a general element of this sum looks like. It looks like this, where we take the sum of elements of this ji's, but only finitely many at a time. That is why we chose elements from these j's in that way. Okay, we chose the indices arbitrarily so that we can have all possibilities, and we chose finitely many of them. So y times a general element of this sum is in I, and that's why y times this is contained in I. But then by the definition of ideal quotient, y belongs to the ideal quotient of I and this ideal. So that way any element in this intersection is also here. So this is also a subset of this. Combining this containment and the previous one, which is its opposite, you have equality. Next. So next we have the notion of the radical of an ideal in a ring. So let I be any ideal in a ring A. I forgot to write that. Okay, so there is the background ring A in which I is an ideal. Then the radical of I is defined as this. It is denoted by this notation r of I, small r of I, and it's defined like this. It's the set of those elements x in the background ring such that some power of x belongs to I, where the exponent n is a positive integer. Now the first thing we are going to see about this Ri is that just like the original I, this is also an ideal, and in fact it contains I inside of it. Let's see how we can establish this. So what we do here, we consider the standard homomorphism from A to the quotient ring of A by the ideal I, phi from A into A slash I. You recall what this thing is. It's the canonical homomorphism which maps any element A in A to the coset of I that element gives us, A plus I. We already know that this map is not just a homomorphism, but actually it's an onto homomorphism, and whose kernel is in fact I. These are things we already know. And we know something else also. We know that we can apply the correspondence theorem for rings here. What does that theorem tell us? It tells us that phi establishes a one-to-one correspondence between the ideals of this second ring and the ideals of the first ring, which contain I inside of them. And how do we have the correspondence? You take any ideal from here, you calculate its inverse image under phi, then you will get an ideal there. That's how the correspondence is set up. And then how are we going to use this here to conclude that this is an ideal? It turns out that the radical of I is just the inverse image under phi of this. What is this? Recall that this is the set of all nilpotent elements in this ring. We already know, we have seen, we saw before that this is itself an ideal in this ring. In any ring actually, the set of all nilpotent elements is an ideal. It is called the nil radical. So this is an ideal here, and you are considering its inverse image, and it turns out that this is equal to this. So by the correspondence theorem, this should also be an ideal in A. And did you notice what I just said now? That not only are these inverse images, not just the inverse image of this one, but the inverse image of any ideal here, not only will it be an ideal in A, but it will, all of them will contain I inside of them. So I is also contained in this. Okay, so that's how we at once know from the correspondence theorem that this is not simply an ideal, but it also contains I. However, how is this true? That also we have to see. So let us next see that. To prove that this is equal to this, we have to show that each one is a subset of the other. Now, without being too specific and without writing too much, let us go through these equivalent statements. Say x is an element in the radical of I. That is true if and only if some power of x is in I, because this is the condition in the definition of Ri. So this is equivalent to this. In what sense are they equivalent? They are logically equivalent. If this is true, then this is true, and if this is true, then this is true. So double implication. But we also know that if this is true, then that is equivalent to this. If x to the power n is an element in I, then the coset of I that this will give is just I, and conversely. But you recall the definition of multiplication in this quotient ring. By that definition, and also noting the fact that n is a positive integer, this is equal to this. Why? But why? When you multiply two cosets, say a plus I and b plus I, what is that multiplication? What does that give you? It gives you ab plus I. So if you multiply n copies of x plus I, you are going to get x to the power n plus I. So that's how you get this. But what does this equation tell you in the quotient ring? This, that x plus I is an element in the quotient ring whose nth power is equal to the 0 element in this quotient ring, because that is I. And that is why by the definition of nilpotent elements, x plus I is a nilpotent element in the quotient ring A slash I. So it belongs to the nil radical of A slash I. And note that all these things that we are getting one after another, we can go back also. Okay, so we have kept that in mind. It's not that we are mindlessly just going on putting this. But this is equivalent to what? Well, because of the definition of phi, phi maps a to a plus I, so x plus I is phi of x, and this is equivalent to x being in the inverse image of this. That is why any element here is also here, and any element here is also here. So that is why these two sets are equal. Now next we have an exercise involving some properties of this radical of ideals. Let's go to that next. Exercise 113, and the first part is this, that the radical of I contains I, and here there is nothing to do actually, because we have already seen that this is true. It comes as a direct consequence of the correspondence theorem, so you just have to write that. So this is done. Next we have part 2. Part 2 tells us that the radical of an ideal is just the radical of the original ideal. So if we keep on taking radical, we do not actually get anything new. The first time we may get something new, but then that's just it. We keep on getting that thing itself. So let's solve this one. So we start the solution like this. By part 1, R of I contains R of I. And that's it. We have got one of the containments that we need to conclude equality. But this looks somewhat confusing. How exactly are we getting this containment simply from part 1? So here we have the explanation. I am showing the explanation like this because I don't exactly think that this should be written. Okay, but anyway, let's see what it is. So we are claiming that R of I is contained in R of I. So we take any element x in R of y. By the definition of I was saying R of y, R of I, then some power of x belongs to I, where n is some positive integer. But by part 1, so this is where we are using part 1, I is contained in R of I. So that is why from this and this we next get that x to the power n belongs to Ri. Now just like Ri is also an ideal, so by the definition of radical, x belongs to this. Now I feel that this is something which you will quickly understand. Because of this, this also doesn't go like this in your mind, systematically like this. You just think of the condition that you need for an element to satisfy so that it will belong to the radical of some ideal. What is that condition? That some power of the element belongs to the ideal. Okay, so you just keep that in mind. So if some power of x is here, then automatically that is here, so that thing will belong to R of I. It may seem like we are really skipping too much, but you will get used to it. Okay, and you will, but anyway, you see, even if you want to write like this, you have to yourself be absolutely sure that what you are writing is really correct. Okay, then you can skip parts like this. It's not a very big matter. There is no unusual twist in this. So that's one containment. Now next let us go for the second one. The second one means the opposite containment unfortunately won't really instantly come like this. But anyway, let's go for it. For the second containment, we take any element y in R of I. So straight away we apply the definition, then some power of y belongs to this ideal R of I. Here this is the radical of the ideal Ri. Okay, but then again, because this is an element in the radical of I, so some power of it will belong to I, where m is some positive integer. But this is actually equal to this. This rule of exponents works here because n and m are both positive integers. You see, a ring is not exactly a field. It's not always a field, of course. So we have to be careful when applying rules of exponents like this. We should not take negative exponents because such things may not exist. The corresponding power may not make sense in the ring. But here we don't have any problem because n and m are both positive integers. You do have to prove this, okay? Not that you have to prove this, but you have to at least know that we need a proof for this which already is there. So now what do we get? Now we get the fact that this power of y, where the exponent is nm is also a positive integer, belongs to I. So by the definition of the radical of I, y belongs to R of I. So any element here is also here, and that way this is also a subset of this. So this and the previous containment then gives you equality. Let us see another part. In this third one we have two ideals I and j, and the claim is that the radical of their product is equal to the radical of their intersection, and that is also equal to the intersection of their radicals. So let's solve this one. So we start the solution first to prove that these two are equal. We already know that the intersection of the intersection of two ideals contains their product. You see, when we introduced operations of ideals, there itself we saw this fact. and that is why the radical of ij is contained in the radical of I intersection j. And here the argument is just like the first containment of part 2, where we straight away wrote by part 1 we have this. So an exactly similar argument lies here behind this. So you can see and you will slowly appreciate that you can't just always keep on writing everything in full detail. But anyway, next we go for the reverse containment. So we take any element x here in this radical, then by definition some power of x belongs to I intersection j for some positive integer n. But then what does this imply? Note that because x to the power n belongs to the intersection of I and j, it is in both I as well as j. So its product with itself will belong to ij by the definition of ij, but that is equal to x to the power 2n. Here we have used the other rule of exponents, and that is also okay because n is a positive integer. Now we have the fact that x to the power 2n belongs to ij, and ij of course is an ideal, and 2n is a positive integer, so x will belong to the radical of ij. So that way any element here is also here. So this is a subset of this. So now you combine this containment and this one and have equality. Next we go for the equality, that this is equal to this. So for the second equality, we first note this. So this part is also like that, first containment of part 2. I intersection j is contained in both I and j, and that is why the radical of I intersection j is contained in the radical of I and radical of j, and that is why it is contained in their intersection. So that way we have got one containment. Now we will go for its reverse, for its opposite. So we take any element y in this intersection, that means here. So then y belongs to the radical of I and y also belongs to the radical of j. So some power of y will belong to I and some power of y will belong to j, where we have positive integer exponents I and j. And then we take the product of these two powers. Again by one of the rules of exponents, this is equal to y to the power I plus j. And this works because I and j are positive integers. Now what happens? You can view this product in two different ways. Actually it's a single product, but you can interpret it in, you can look at it in two slightly different ways. You can view this product as the product of this element of I, of the ideal I, by some ring element y to the power j. So because I is an ideal, this should belong to I. But you can also view this product as the product of this element of the ideal j by some element of the ring which is y to the power I. Because j is also an ideal, so this product should belong to j as well, and that is why this belongs to I intersection j. But then this belongs to I intersection j, and I plus j is a positive integer, so this will belong to the radical of I intersection j, and that way any element here is also here. So this is a subset of this. Now you combine this one and get equality. So that's it. Actually there are three more parts which we will solve in the next commutative algebra video.